let's talk about force, work, and kinetic energy. Energy has always been a focus of this class, and now we're going to relate it to forces. We're going to start by looking at the equilibrium condition, and the total potential energy of a system is at a minimum in equilibrium. So the types of potential energy we've talked about so far, we've talked about gravity and springs. Gravity, just mgy, and springs 1/2 kx squared. Now, if you're looking for a minimum, you know that the first derivative has to be equal to 0. That means that this is going to be a flat spot, so it's not going to roll. All right. Then, if you want a stable equilibrium point, you want your second derivative greater than 0, so you have this concave up curve. So that if that little red ball goes back and forth, it's just going to go and eventually come to rest right in the middle at that stable equilibrium point. So previous in the class, we've talked about how the derivative of kinetic energy with respect to position gives you mass times acceleration. Well, let's see what happens when you take the derivative of potential energy with respect to position. Well, if you get multiples, you just add them up, and the contributions will still equal 0 because you're at equilibrium. And we're going to define this as a force, this change in potential energy with respect to x. So it's related to the slope of the potential energy curve. What's that minus come from? Well, good question. Forces act to reduce potential energy of a system. If you have a ball, it'll fall down. And why? Because it reduces gravitational potential energy. So our equilibrium condition becomes the change of potential energy with respect to x, which is equal to your forces, equals 0. Or that there's no force acting on this. The potential energy with respect to x isn't going to change. Force is measured in newtons, named after this guy, Isaac Newton. And if you're looking for 1 newton of force, accelerates a 1 kilogram object 1 meter per second squared. If you're curious, like, what's a newton? We don't really talk about that every day. Well, it's about the weight of 1 apple, which is convenient because as the story goes, it bonked this guy on the head. Not the full story, but if you ask me in class, I'd be happy to share that with you. And now let's talk in words because words are great. So a force is just a push or a pull. All right, something has to do the pushing or pulling, and you have to push something or pull something. It is a vector. That's very important. So it's got a direction and a number, and it results either from a contact or from a long-range interaction. We'll talk about field forces like gravity, and we'll talk about contact forces like if a spring's pulling or people are pushing. We've talked a little bit about conservative forces, like this gravitational force. Conservative forces are just associated with potential energy. So we look at the potential energy of gravity, take its derivative with respect to x, which is position, and we get, oh look, the force of gravity is minus this term right here, which if you plug in the numbers for the mass of the Earth, you get minus mg, where the minus means things fall down, or towards the center of the Earth. If you look at springs, here's our spring potential energy. We'll take the derivative with respect to position, and we wind up with this, which you may recognize as Hooke's law. It's the force that a spring pulls. Notice this minus sign, because if you've got a spring, if you stretch the spring, well, stretch it out, then this block on the end is going to go to get back to this nice little equilibrium point. Forces restore objects to equilibrium. They pull them back towards the equilibrium point, at least when they're associated with potential energy. Now what happens if we have non-conservative forces? Non-conservative forces behave a little different. They're external pushes or pulls. So if you have a box, you need something external to push it, like a person. Tension in ropes, okay, we talk about ropes, and the normal force. Now when we say normal to a surface, we just mean perpendicular. And then friction, which is always opposite of direction of motion. So friction opposes the motion of the object. We'll talk more about that in a little bit. So forces do work, whether it's a conservative or a non-conservative force. To look at the work, we're going to look at a force applied over a distance. Now, wait, what's this little dot mean? That dot is a dot product, aptly named, and all it means is that you only care about the force, in this case in the x direction, times the displacement in the x direction. So if we look at this, this force times displacement is just the area under a force displacement graph. But let's see what happens to our signs. So the first thing we should do is define which way is plus x. I'm going to define to the right as plus x. Friction is going in the negative x direction. We indicate that by this little x with the caret on top, called a hat. because it just points direction. Well, it looks like an arrow, so it points direction, and it just sits on top, so we call it a hat. So you'll notice that this force is negative, the force of friction, times positive, delta x, because it's in the positive direction, and your work is going to be less than 0, which makes sense because it's friction, and friction takes energy out of the system. Let's work a couple examples now. Here I have a person pushing a box. We're pushing a box. We'll define this as the plus x direction. And then we will say that we only care about this x direction, which means I need to figure out how much of this force goes in the x direction. Inner trigonometry. Since I want this adjacent side over here, I know I'm going to use cosine. So 200 newtons times cosine of my angle, 30 degrees in this case, times how far the box moved on the plus x direction, gives you a total of 520 joules. Not too shabby for a day's work. This is work done on the box, so it's going to increase the energy of the box. Example 2. So now we've got the same thing, except now we've got a force acting in the x and the y direction. But if you pay attention, it's only moving in the x direction. Well, since it's only moving in the x direction, we only have dx, which means who cares about that y component? You're not doing any work in that direction. So we'll integrate with this. Integrate 2x cubed. Integrate the x cubed. Evaluated our conditions, and you get 2 newton meters, or 2 joules. Keep in mind, we threw out the y component because it is just simply fx dx. Same way that if you lift a box up and move it this way, gravity does no work because gravity points down. Okay, so if this is force of gravity, gravity would do no work if you're moving the box left and right because they don't point in the same direction. It's an interesting piece. If you have any questions, please let me know, and I will see you in class.